There is a dead star 60 light-years from Earth that is made almost entirely of crystal. Not metaphorically, not in the way that science sometimes uses the word crystal loosely to mean any ordered structure. A crystalline lattice, carbon and oxygen atoms locked into a rigid, repeating geometric pattern extending from the core to the outer layers of an object roughly the size of Earth, but containing the mass of the Sun. A solid, crystalline sphere of matter so dense that a teaspoon of it would weigh approximately 15 tons on Earth's surface. It is called a white dwarf, and it is not unusual. Not anymore. In 2019, the European Space Agency's Gaia mission, the same satellite that revealed Schultz's star's ancient close approach to our solar system, released data on white dwarfs in our Naylor stellar neighborhood that changed how astronomers understood the final state of stars. Analyzing the temperatures, luminosities, and ages of thousands of white dwarfs, they found a pileup. Too many white dwarfs clustered at a specific temperature range, cooling more slowly than the models predicted, releasing extra heat that the standard picture of stellar death did not account for. The extra heat was the signature of crystallization. As white dwarfs cool below a certain threshold, roughly 10 million degrees at their cores, the carbon and oxygen ions that make up their interiors can no longer resist the pull of electrostatic forces. They begin to lock into place. The liquid interior solidifies from the center outward, releasing the latent heat of crystallization the way water releases heat when it freezes. A star does not burn out. It freezes. And the process is not rare. Gaia's data suggested that the vast majority of white dwarfs in our galaxy have already crystallized or are currently crystallizing. Not a fraction. Not an exotic subclass, most of them. The galaxy is full of crystal stars, and several of them are close enough to have names. To understand what a crystalline white dwarf actually is, you need to understand what it came from. A white dwarf is the remnant of a star like our Sun, a medium mass star that exhausted its nuclear fuel, expanded into a red giant, shed its outer layers as a planetary nebula, and left behind a compressed core containing most of its original mass. The core is supported not by nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons in the dense matter from occupying the same quantum states, creating an outward pressure that holds the object up against its own gravity without any burning at all. No fusion, no energy generation, just a hot, dense ball of mostly carbon and oxygen, slowly radiating its residual heat into space. This is the fate of approximately 97% of all stars in the Milky Way, including our Sun, in approximately 5 billion years. The red giant phase, the planetary nebula, the exposed core, and then a white dwarf, cooling slowly over billions of years. Cooling, always cooling, radiating heat into an expanding universe that grows colder over time. And as it cools, something happens inside that nobody fully appreciated until Gaia measured it directly. It crystallizes. The crystallization begins at the core, where the pressure is highest, and the temperature, counterintuitively, is where the phase transition threshold is first reached. Carbon and oxygen ions, stripped of their electrons that move freely through the dense interior, begin to settle into a body-centered cubic lattice, the same geometric arrangement that iron atoms adopt in steel, except that this lattice extends across an object the size of Earth, forming a single coherent crystal structure of almost unimaginable scale. A crystal the size of a planet. As the crystallization front moves outward from the core over billions of years, the latent heat released slows the cooling process. The white dwarf stalls at a specific temperature range, too warm for its age, lingering at a luminosity it should have left behind millions of years ago, releasing the stored energy of a phase transition that is happening one atomic layer across the interior of a dead star. Gaia saw this stalling in the population statistics. Too many white dwarfs at the right temperature for crystallization, a traffic jam in the cooling sequence, exactly where the physics predicted it, and in exactly the proportions the models calculated. The confirmation was indirect but unambiguous. The crystal stars are real. The process is real, and it is happening right now in white dwarfs throughout the Milky Way, including several within a few tens of light years of Earth. The nearest confirmed white dwarf is Sirius B. Sirius, the brightest star in the night sky, the star that marked the flooding of the Nile for ancient Egyptians, the star that navigators have used for millennia, is not one star. It is two. Sirius A, the brilliant blue-white star visible to the naked eye, and Sirius B, its white dwarf companion, orbiting each other every 50 years at a distance similar to the distance between our Sun and Uranus. Sirius B is approximately 8.6 light-years from Earth. It is roughly the size of Earth, containing approximately 1 solar mass. Its surface temperature is currently about 25,000 degrees, hot by everyday standards, but cool for a white dwarf. It has been cooling for approximately 120 million years since it became a white dwarf. At its current temperature and mass, Sirius B is approaching the crystallization threshold. Its core may already be partially crystallized. Within the next few 100 million years, a short time in stellar terms, it will be a crystal star, its interior locked into a rigid lattice from core to surface, releasing its latent heat slowly into the space between it and its brilliant companion. 8.6 light-years away, the same distance that separates us from the brightest star in our sky.
A crystal forming in our stellar backyard. But Sirius B is not the one heading toward us. There is a white dwarf called Maanen Star. It sits approximately 14 light-years from Earth, close enough to be among the nearest 20 stars to our Sun. It was discovered in 1917 by Dutch astronomer Adriaan van Maanen and holds a specific distinction in the history of astronomy. It was the first isolated white dwarf ever identified. Maanen Star is old, significantly older than Sirius B. Its surface temperature is approximately 6,000 degrees, cooler than our own Sun's surface, which sits at about 5,777 degrees. It has been cooling for billions of years. At 6,000 degrees surface temperature, Maanen Star is cold enough that its interior is almost certainly crystallized, not partially, not in process, done. A completed crystal, billions of years in the making, 14 light-years from where you are sitting. And Maanen Star has a proper motion, a trajectory through the galaxy that carries it on a path through our stellar neighborhood. It is not on a collision course. It will not pass within the Oort cloud in any time frame that current calculations can confirm, but it is moving. All stars move, and its motion carries it through a region of space that our solar system also inhabits. A crystal star, 14 light-years away in our neighborhood, moving. Here is where the story becomes something more than a description of stellar physics. In 2019, the same year that Gaia confirmed crystallization in white dwarf populations, another team, using spectroscopic data from white dwarfs in our galactic neighborhood, found something in their atmospheres that should not have been there. Heavy elements. White dwarf interiors are crystallized carbon and oxygen. Their thin outer atmospheres, under the intense surface gravity, approximately 350,000 times Earth's surface gravity, should be almost perfectly stratified. Heavy elements sink rapidly in a white dwarf atmosphere. The settling timescales for elements like calcium, iron, and silicon are thousands to millions of years, an instant in astronomical terms. The surface of a white dwarf old enough to have crystallized should be nearly pure hydrogen or helium, all heavier elements long since sunk into the interior. They were finding calcium, magnesium, iron, silicon in the atmospheres of old, cold white dwarfs that by rights should be pristine. The conclusion was unavoidable. Something was delivering these heavy elements from outside. Something was falling onto the surfaces of these white dwarfs continuously, replenishing the heavy element content faster than it could sink. The something was planetary debris. White dwarfs are surrounded by the remnants of their planetary systems. When the parent star expanded into a red giant, the inner planets were destroyed, but outer planets, asteroids, and comets survived, disrupted into new orbits by the loss of the star's mass during the red giant phase, slowly being perturbed by the gravitational influence of surviving planets, occasionally being nudged into trajectories that bring them close enough to the white dwarf to be shredded by tidal forces and fall onto its surface as dust and gas. Polluted white dwarfs with heavy elements in their atmospheres, are not rare, they are common. Approximately 25 to 50% of all white dwarfs show this pollution signature. The crystal stars are not just remnants of stars, they are remnants of entire solar systems. The debris of the worlds that once orbited them is still falling onto them billions of years after the star died, leaving traces in the atmosphere that spectroscopes can read like a chemical record. Maanen Star is a polluted white dwarf. Its atmosphere contains calcium and other heavy elements that should not be there. Debris from its former planetary system, whatever orbited Maanen Star when it was a living main sequence star before it expanded and died and crystallized, is still raining onto its surface. We cannot see those planets, we cannot see the asteroids. What we can see is their chemical signature written in the absorption lines of Maanen Star's spectrum, readable from 14 light-years away by instruments that were not built until a century after the star was first identified. The dead star is surrounded by the remains of worlds. Crystallized, cold, ancient, still accumulating the debris of a solar system that died billions of years ago. There is a white dwarf that deserves its own moment in this accounting. BPM 37093, 50 light-years from Earth, a white dwarf approximately the mass of our Sun, surface temperature approximately 12,000 degrees, cooling steadily toward the crystallization threshold and possibly already past it. Models suggest that more than 90% of its interior has crystallized. Astronomers who studied it named it Lucy, after the Beatles song, after the diamond, because that is what it is. A diamond the size of the moon, a crystalline mass of carbon at the scale of a small planet, orbiting at 50 light-years with no planetary system we have detected and no companion star. Just a crystal, alone, cooling.
Lucy has a proper motion. Everything moves in the galaxy. Its trajectory carries it through the local stellar neighborhood on a path that, over millions of years, will change its distance from our Sun. Not dramatically, not toward a close approach that threatens the Oort cloud the way Gliese 710's trajectory does, but moving. The most famous crystal star in our galactic neighborhood is in motion, as are all of them. What does it mean that the galaxy is full of crystal stars? It means the end point of stellar evolution, the final state of most stars that will ever exist, is not a burned-out ember slowly fading to darkness. It is something stranger and more structured than that. A phase transition, a solidification, an object that begins its existence as a nuclear furnace, spends billions of years burning hydrogen and helium, expands and dies and sheds its outer layers, and then, in its final cooling, undergoes a transformation at the atomic level that turns it from a fluid into a solid. The stars do not just go out, they freeze. And in the freezing, they release heat,
billions of years worth of latent heat stored in the phase transition, radiated slowly into space as the crystallization front moves outward from core to surface over hundreds of millions of years. The universe is littered with these objects. More than 10 billion white dwarfs in the Milky Way alone, most of them older than Sirius B, cooler than Maanen Star. Some of them so cold they have become what astronomers call black dwarfs, white dwarfs that have cooled completely to match the temperature of the surrounding universe and emit no detectable radiation. Except that no black dwarf is confirmed to exist yet. The universe is not old enough for any white dwarf to have cooled completely. The oldest white dwarfs, formed from the first stars to die in the Milky Way, are still warm enough to detect, still radiating, still releasing the last of their heat into an expanding, cooling cosmos. The black dwarfs are coming. In timescales that make the current age of the universe look brief, the crystal stars will finish cooling. They will go dark. The galaxy will fill with invisible crystalline objects, perfectly ordered atomic lattices, the size of planets containing the mass of stars, drifting silently through interstellar space with no light to reveal them. Dark, cold, perfect. The sun will become one of these objects. Not for 5 billion years, not before the red giant phase that will expand the sun to engulf Mercury and Venus and possibly Earth. Not before the planetary nebula that will scatter the sun's outer layers across a region of space several light years wide, producing a glowing shell of ionized gas that will fade over tens of thousands of years. But eventually, after all of that, what remains at the center will be a white dwarf, a compressed carbon-oxygen core, roughly the size of Earth, containing approximately half the sun's current mass, radiating its heat into space. And as it cools over billions of years, it will crystallize. The sun will end not as ash, not as darkness, but as a crystal, a rigid, ordered structure of carbon and oxygen atoms locked into a geometric pattern that will persist for longer than the universe has currently existed. Every atom of carbon in that crystal was fused in the sun's core during its main sequence lifetime. Every atom of oxygen, the nuclear fusion that powered 4 billion years of sunlight, the light that drove photosynthesis, that warmed the oceans, that made life possible on this planet, will leave behind its products, locked into a lattice, forever. The crystal will contain the chemical record of everything the sun ever burned. Look up at Sirius on a clear night, the brightest star in the sky, blue-white, brilliant, flickering near the horizon in winter, a star so luminous that ancient civilizations built calendars around its heliacal rising. And know that 8.5 light years away, orbiting that brilliant star every 50 years, there is an object the size of Earth that is quietly, over millions of years, turning to crystal. You cannot see Sirius B without a telescope. Its light is overwhelmed by the glare of Sirius A, but it is there, cooling, crystallizing, building its lattice one atomic layer at a time, releasing its latent heat into the space between it and us. The nearest crystal star is not in a distant galaxy or at the edge of the observable universe. It is the companion of the brightest star you can see with your naked eye. And beyond it, in every direction, in a galaxy containing more than 10 billion white dwarfs at various stages of the same process, the freezing is ongoing, has always been ongoing, has been happening since the first massive stars died billions of years before our sun ignited. The universe is not running down into darkness and heat. It is running down into something colder and stranger than darkness. It is crystallizing, star by star, atomic layer by atomic layer, building a structure that will outlast everything that is currently alive in the observable universe. And the nearest example of that structure is close enough that on a dark night with a telescope, you could find it if you knew where to look. 8.5 light years away, already forming, already becoming what all stars eventually become: a crystal in the dark.